All right, welcome. Let's get started. Okay, so just as a couple of reminders to begin, your next homework assignment is due at the beginning of class on Thursday, and you're going to be submitting that on paper, unlike the first assignment which you submitted electronically. Now, as I showed you during our first class, there's a sample assignment that's available on MU Online, and you can look at that for a formatting example. And so please follow the same formatting example that you saw on the example that's on MU Online. And you need to show your calculations in detail, especially on problems 5 and 6, which are some conversion problems. All right, now I've got something to show you. It's a conversion, it's like a page full of conversion factors. I'm going to put that available on MU Online so that you can refer to it. It's all in one place. It comes from the reference manual that's provided for the Fundamentals of Engineering exam. And if you're wondering why we didn't have class on Thursday, it's because I was down in Clemson, South Carolina, helping develop questions for the FE exam. And so it's something that I think almost all of our seniors take to become on the road to licensure. And it includes this page full of, let's see, can I do full page? It's not jumping out at me. Anyways, it'll be there available for you to print off on MU Online. It shows the conversions for between BTU per hour and watts, which I was looking over the assignment before I came in, and that's one that you're going to need to have. By the way, could you switch off your monitors if you haven't already, just to avoid the distractions during the lecture part. Anytime I hear clicking, I know that someone isn't probably paying 100% attention to the lecture. Thank you. Okay, so this conversion factor is really important, and getting an early exposure to it, I hope, will make it easier for you on the day that you eventually do take the FE exam, if you know kind of how to use the conversion factor and where it is in the reference manual and so on. So if you haven't yet completed the assignment, then that may be a useful resource, and it'll be posted on MU Online for you to print. Any questions so far related to the announcements? Yes?
I just have a question on the homework.
Okay.
Number 3 and 4 have the 2 tables for the different pages. Do you want those on the
Right, so you're asking, should you write on the handout itself, right? Yeah, don't write on the handout itself. You should put that on the engineering paper. That's a really good question. I'm glad you asked that. That's something I had meant to mention but had forgotten about. So hopefully you'll be able to do that all semester long. Remember the things that I forgot. All right? Good question. Now, speaking on the subject of homework, I've scored your first assignment, and a few people uploaded a file that was empty. There was more than one person that did that. And so I've put in some comments, like I wrote a short comment to everyone in addition to the score. So if you go into the gradebook on MU Online and see that your score on the assignment was 0, it might be that whatever file you uploaded was corrupt or a blank document or in an incompatible file format. I left instructions on what to do in that case for the handful of students whose files didn't come through. And the rest of you, you can look at the comments that I wrote. So today we're going to be talking about linear interpolation, and then just a very first and brief exposure to some concepts that exist in programming, which we'll get to later in the semester. So unless there are any questions, we'll go ahead and start talking about linear interpolation. All right. Now this may be a reminder to some of you, but then I know that there are a lot of other people who've never learned about linear interpolation before. And the reason I know that is that I teach a follow-on class to this one. It's called Engineering 221. Engineering Computations, and you have to use linear interpolation in that course. And I was amazed at how many students had forgotten linear interpolation. And those are all students who presumably had already been through this course. So this is an important subject and one that we'll come back to a few times during the course of the semester. I'm glad to see a lot of you taking out paper to take notes. That's great. As a reminder, I'm recording this lecture, and so if there's any concept that we skip over a little too quickly, or if you need to refresh your memory, as you're working on the assignment, all of the links for these recordings are available on MU Online. There's a different link for each lecture. And so you can just go to our course website and then find the link to the video. And so if you're taking notes and you couldn't quite get the entire slide, you can let me know and I'll come back to it. But if we don't have time to do that, you can always come back to the video itself. All right, so let's look at this figure that's provided here. On the horizontal axis are two x values, and then on the vertical axis are two y values. And they're designated 0 and 1 for the two values. Now, what we do with linear interpolation is we're saying we want to find out some value that's in the middle. And the typical thing in linear interpolation is that your input values are expressed on the horizontal axis, what's called an independent variable, and the output, or the dependent variable, is displayed on the vertical axis. And so right now there aren't any numbers or units associated with this figure, but it illustrates the idea that if you have 2 points and you want to find out what's the y value for some value in between here, you could just, on a curve, follow the line straight up until you hit the line that connects these 2 points. And then you go sideways to find some intermediate value. And this is something that you'll do a lot, and sometimes you won't even know that you've done it, but the tables you use will be based on linear interpolation. And so it'll be incorporated into your data in the background in a way that you may not actually even see. Here's the formula that you can use when you're doing the calculations. I mean, it's easy if you've got a graph provided already, but sometimes you're not given a graph, but rather you'd be given a table. And then it's up to you to interpolate given that table. And so here's what you do. You identify with the given data what are the x values and what are the y values, because they're not always in the problem statement going to be called x and y. They may be given different variable definitions, like it might be the grains of weight and the dollars that you're spending if you're buying a chemical, for instance. That could be on one axis is the input value, and so if you're buying chemicals, then we're saying the price that you pay is dependent on the mass that you're buying. And so mass would be on the horizontal axis, and the price would be on the vertical axis. So you identify what is the known y0, y1, the known x0 and x1, and then here the value x that we put in, that's the only value here that doesn't have a subscript, that would be the input value that you're trying to find an output value for. So this seems pretty abstract until you actually get to solve a problem with it. If you haven't written down anything else, please be sure that you write down this formula, because you're going to use it in an in-class example in just a moment. Let me give you a moment to finish writing that formula. All right. So here's an illustration. I'm going to do these calculations on the board to give you the general idea, and then there's going to be a similar example following this, which you can use to practice the concept. All right, so here we have a table. This looks to me like structural analysis stuff. Honestly, structural analysis, it's been a long time since I took any classes related to that, so I'm not honestly even sure what these values are. But it doesn't matter, because all we're trying to do is interpolate. So in this illustration, we want to find out what is the value of n sub c if we have this phi of 2.3 degrees. So here is our x values. These are the input values that we've got, and here are the output values. Just at first glance, can you tell me what is the answer between? And we know the bounds that it's between, right? So what's the outer range of possibilities for our answer? We know that n sub c is between what two values? What is it? So here is 2 and 3. We want to find out what is it for 2.3. Okay, so here is the n sub c values, and so our answer is going to be somewhere between 6.3 and 6.62. So at first glance, we know that if our final answer isn't between 6.3 and 6.62, we've done something wrong. All right, so now let's go through the calculations and check this for sure. We have our naught value is 2, and our 1 value is 3, and then n sub c naught is 6.3, n sub c 1 is 6.62. Now, in this figure that we saw before, we said something goes on the horizontal axis and something goes on the vertical axis. I want to draw a little sketch. What should I put on which axis of these data values that we've already got from the table? Anybody feel like they have an idea of what goes where for this problem? Like I'm going to put one thing, if I want to label my two axes, what should be on the horizontal and what should be on the vertical? All right. That's correct, yes, because that's our input value. So we put that on our input value, and then the output, what we're trying to find, is the n sub c, right? Feels a little warm in here. Oh, it seems like they've fixed that off. All right. So we could graph the data. Here's 1, 2, 3. So we have on this axis, maybe here is 6, 6.3, 6.6. And so here at 2 and 3, we've got the values, and we're going to interpolate linearly between them. So that's what our graph should look like. And we're trying to find out what is it for 2.3. So it's over here somewhere, going up and going over like so. All right. So graphically, it already matches what we kind of estimated, was that our answer is going to be between 6.3 and 6.62. Now I'm going to label these values. We're going to call this is our x naught in the formula. This one is our x1 value in the formula. In the formula, let's have this one be our y naught, and this is our y1 in the formula. And so here was the formula that we used. Let's substitute the values in. It's going to be n sub c, which is the y value here that we're solving for, the output, is the y naught, which was 6.3, plus 6.62 minus 6.3 divided by 3 minus 2, and then multiply that by 2.3 minus 2. So essentially what we're doing is we're saying our value over here on the vertical axis is going to be at least this y value, and then it's some distance above that. And the distance above it depends on the slope, and then the distance beyond the x naught to our point of interest. So that's how we interpret this equation. This is our slope component, and this is how much delta x we've got. So this is our base y. And when we crunch those numbers in the calculator, how many of you have already purchased the recommended calculator for the semester, the Casio? Have you got it with you here today? Grab that calculator out. You should have your calculator at all times. When you sleep, it should be under your pillow, right next to your 45, all right? Because you never know which one you're going to need. need? In the middle of the night, someone knocking on the door. Could be an intruder. It could be somebody who needs calculations done. All right? That's a fantasy, not a dream. Right? All right, so get your calculator out and calculate. So when you do these calculations, the slope is 0.32. Obviously, the delta x is 0.3. So what do we get for our n sub c value? My compliments for putting away your phones. I can't see any phones right now, and I'm just delighted about that. In fact, I'm wearing a watch today, so I don't have to get my phone out. An uncomfortable plastic watch, just so I can set a good example. All right, anybody do the calculations? What'd you get? All right, good. So you got that this y value 6.396. Now, from the recorded lecture, we were talking about rounding. In this example, what should we round our final answer off to after we've got this answer in the calculator? Well, based on the data that we have to begin with, we need to round this off to the nearest hundredths. And so we would display that as 6.40. So the n sub c is 6.40, and we do the reasonableness check. It is between our initial guess of what we thought. And if we look here on the figure, between 6.3 and 6.4, but it's going to be lower than the midpoint between them, right? Because the midpoint would be 6.45. It's not going to be quite that high because it's only 6.3 and not 6.5. I'm sorry. It's only 2.3 degrees and not 2.5 degrees. Okay, so here's the substitutions and the calculations that we just did. And just to reiterate the importance of following that standard sort of solution approach. Here's the example that shows how you need to do it for the homework. I don't know how to close that. All right, so we start off by summarizing the problem. Find n sub c for phi equals 2.3 degrees. We have our given data. Is there a diagram we can put together? So I did a little sketch where you can find out what's the input and what's the output that we're trying to find. Now, I even mentioned this assumption that the data varies linearly between points. And linear interpolation sometimes is inappropriate because if your actual data follows a curving trend, if you try and do a linear interpolation between points, you may introduce some error. But here we're assuming, and I've stated the assumption, that the data varies linearly between the points. Mentioning the governing equation, then the computations, and finally rounding off the answer. So this is the format that you should follow on your assignments, where you're boxing the final answer, you're drawing an arrow and writing the word answer, labeling the steps of the problems. And are there any questions on the illustration? Okay. Well, I want you to have some practice with this. And for those of you who don't have a calculator with you today, there should be a calculator emulator on these computers here. Let's see if I can find the emulator. Well, you can use this calculator, but there's supposed to be the Casio. Let's see. Oh, wait. No. They said that they'd installed a Casio emulator on the machines in this classroom, but that might not have been, oh wait, here it is, Casio Emulator. All right, so the nice thing about this is it's like sort of a computerized simulation of the calculator that you're supposed to use this semester. Okay, so you just click on the buttons like that. So you don't have to get your phone out if you don't have your own real Casio with you today. You can use the emulator. Okay, so here's what I'm going to do. I'm going to pause the recording so you can work on the following example. Same table, but now we want to find out the n sub q for a phi of 3.7 degrees. All right, so same method, same formula, but I'd like you to see if you can find the answer for this one. Let me pause. All right, so here on the whiteboard, I've written down the x and y values. How did I know which was the x and which was the y? Well, in this table, we're going to say that the x is the input values and the y's are the output values. And so this n sub q is dependent on what value of phi you choose, right? So the n sub q is our y. And so I picked the upper and lower value that bounds where is the x value we're interested in. So we have an input value of 3.7 for phi, so that's between 3 and 4. So those are our two x values, and then the y values are 1.49 and 1.35. And maybe that's the hardest part of a problem like this, is just identifying what variables to use so that when you plug it into the equation that you get the right answer. So did anybody else get 1.45 for their answer? Good. And that's about what we'd expect. If you just look at it, it's going to be between 1.35 and 1.49. But it's going to be closer to the 1.49 side of things. You know, why is it going to be closer to this one than that one? Well, because 3.7 is closer to 4 than it is to 3. So that's the essence of linear interpolation. Any questions? All right. Enough about that for now. Let's talk a little bit about software and programming. We don't actually get to this until later in the semester, but it's useful to talk about now because a lot of what we do on paper with the calculators and what we're going to do with Excel kind of mirrors the logic and the thinking that's behind the programming we'll do later on when we use MATLAB. Now there are some specific software that have been developed for very narrow applications. For instance, in hydraulic engineering, which is what I do, there's a software package called HEC-RAS. And what it models is water surface profiles in rivers. So the Ohio River, for example, it's very important for the Army Corps of Engineers who manages the river to know what the water level is going to be like upstream of stations where they have actual gauging instruments. Because they don't measure what's the depth at 1-foot intervals up the river. You know, that would be cost prohibitive. In fact, they don't even measure it every mile. Gauging stations where they physically measure how deep the river is, they may be 20 or 50 miles apart. And what they do in between is they do a form of interpolation. But linear interpolation would work horrible for a river. And so they have to do very sophisticated calculations that take into account the width of the river, the quantity of the flow rate, and a lot of other factors like the roughness of the channel. And so HEC-RAS does that. It's a water surface simulation program. A lot of these other software packages have also been designed with engineering applications in mind to try to increase the speed at which engineers can work. And often they're not doing anything that you can't do manually, it's just that they do it faster. Now, there are sometimes situations where we don't have a pre-existing package to solve exactly the problem that we're working on. For example, there isn't a computer program that exists only for linear interpolation, like the examples that we just did on the board. And so what you could do is you could write your own software for the specific application that you have in mind. And here's a list of just some programs, and there's hundreds of other computer programming languages that allow you to customize and develop programs that solve whatever problem you've got in mind. And MATLAB is one that's used a lot, especially in mechanical engineering, because of its flexibility. Anybody here have some past experience with programming? A little bit? Great. Each one has its own advantages, but there are some common trends regardless of which language you program in terms of the logic and the fact that every software program has inputs, things that come into the program. So I was talking about HEC-RAS and how it monitors the river elevations. Well, to do that, it has to know the depth of water at one location, and it has to know other things like the flow rate of the water, the width of the channel, how wide is the channel below the surface in addition to at the surface itself. And so there's a lot of data that you have to type in before the program will run. And then it saves it behind the scenes, someplace you don't see. It's saving the data that you put in as variables. All computer programming languages have a way of performing logical sequencing, like if-then statements, or loops that count the number of times something has been done. All computer programming languages also have the ability to perform calculations, and so the formulas maybe are user-entered, or they may be pre-existing formulas that exist as equations in a library that the software holds on to. And then finally, all programs have outputs, whether it's a print on the screen or to a PDF file or just results that are displayed on screen. Otherwise, the software wouldn't really have any point if it didn't have an output or the user couldn't see the output. So these are some commonalities. And what we'll do a little bit at the beginning of our programming is start to think about how to write computer programs in a pseudocode, like thinking about the logical structure that's required for a computer program. And one useful way to begin that process is with flowcharts. And flowcharts are, I'm sure everybody's seen flowcharts like this. It's a way of stepping you through the flow, the decision matrix of what to do in a certain situation. And it being so discrete allows a computer, which doesn't have any judgment, to know how to proceed in each case. It has to be a yes or a no. Computers don't really do good with maybes. It has to be a binary option. Now, there may be some ambiguity within a series of decisions that you can break down into smaller yes-no decisions. But this flowchart you can take and then translate into something called pseudocode, which it's not quite yet a program that's going to actually compile and execute, but a pseudocode is a way that you can start, it's a beginning point that then you can put into the specific terms and language that the computer software you're using requires. So let's look at an illustration of the programming symbology. Now, this isn't always, these symbols aren't always used, but it is useful to point out that the decision point, this is pretty common. The decision point using the diamond shape for that is pretty common, as if we go back here, you're having to go one direction if it's yes, another direction if it's a no. So we see how that diamond is being used. The boxes indicate program steps, a start or finish, and then inputs and outputs are sometimes shaped a little bit differently. Now, the flowcharts are useful just for breaking down a task into its pieces, but the flowcharts alone don't necessarily allow you to begin writing a computer program. And so we'll look at the pseudocode in a minute. But here's kind of it's attempting to be funny, an illustration of how every problem an engineer faces can be solved by duct tape or WD-40. So have a look at that. So if it's moving and it shouldn't, you tape it down. like your windshield wipers if they're broken, or, and if it's moving, if it's not moving but it should be moving, then you spray WD-40 on it. So those are your two tools and you're all set. So here's how we would translate that using the symbology that was on the previous slide. When we have a decision point where we have to go one direction or another, we're using the diamond shape. So does it move, yes or no? Should it move, yes or no? We get to no problem if it's not moving and shouldn't be moving. And then finally, to end. You can see that regardless of the path, it always results in end. Now, here's how that would look in a pseudocode. A pseudocode doesn't necessarily depend on what programming language you're using. You can take a structure like this and translate it into whatever particular language it needs to be in. You can see here we've indicated the start of the program. Each of the lines is numbered, maybe just for reference. Not all programming languages require you to number the lines. Some do. But the indentations here indicate a decision point. And so the if and else, these are illustrations of logical decisions that have to be made. It's a dependency statement. If the object moves as yes, then what under it will kick in. If the object doesn't move, then it goes to the else, and then what's underneath the else will start to execute. And so the first thing you have to diagnose is the object moving? So let's say that the object is moving. So the next thing is there's another if-then statement, if-else. And so if the object should move, then this is the take no action, because it's moving and it should be moving. So take no action, and then the program terminates. If the object should move but it's not, now there is no no in there. You see how there isn't if object should move equals no? The reason why we don't need that is because if the yes statement doesn't trigger, then the else takes over. And so the no is sort of implied by the else. And so if it wasn't a yes, then that means it has to be no. And so if it's a no, then apply the duct tape. Okay, now if the object moves equals yes didn't apply, then the else would take over and it would be the same idea until we get to the program end. Now, when I was looking at this to prepare for class today, line 14 puzzled me a little bit because I thought maybe it was an excessive end, but then I realized it's not excessive. This end replies to the entire else statement, the second if the object should move. This end only applies to the take no action. So we can, just through a series of tabs, if-then statements, program a computer that would be able to understand that same flowchart that we put together earlier. All right. Now, it's only 11:38. Our class is scheduled until 12:15. As I mentioned at the beginning of the semester, this class is specifically designed so that we've got plenty of time during our actual meetings together for you to work on in-class examples and even the homework assignments. And so I'm going to stop the recording. You're welcome to stay and work, in fact encouraged to stay and work on the homework assignment so that you don't have to do it outside of class. And you can collaborate with your classmates, but the homework assignments need to be an independent effort. I'll be circulating around to answer any questions that you might have, and just because people might leave at various times, I'm going to give you these announcements one more time. The assignment's due at the beginning of class. It needs to have the cover page as shown in the example. It needs to follow all of the same formatting requirements as that example, and it's especially important that you show your calculations on problems 5 and 6, and that conversion, I'm going to put the conversion page online right now so that if you want to take a look at those conversion factors, those will be available on MU Online. All right, The time is yours to start on the assignment.